Let's go over the continuous math question that I did. In this question, we have, in the first part, it's testing Taylor's theorem. Suppose that f is a function from R to D to R is convex. So this is a key info. If it gives us that's convex, okay, we know that the second derivative is greater than zero, right? And then all its second partial derivatives exist. Use Taylor's theorem to prove that for all xy that are um, d-dimensional, we have this thing holds. So yeah, this is looking like Taylor's theorem. So we're going to use Taylor's theorem. Um, yeah, the thing we want to prove. Okay, here. This is Taylor's theorem. This thing over here. And we see that it's awfully similar, except that the only difference is that we have this extra bit over here, right? The second term. But we know that f is convex if its Hessian is positive semi-definite for all z. So by positive semi-definite, we can have um, something of this form, something of the Vt times the Hessian of that of V is greater than or equal to zero. This is just the definition of positive semi-definite. And then inside this scenario, we just have our v is equal to y minus x as the vector. So hence we can show that the second term over here is greater than or equal to zero. Hence the greater sign holds for the thing. So A is very straightforward, I'd say, because the form is the same and it tells you to use Taylor's theorem. So there's not much kind of things to do. In part B, we have if f and g are convex univariate functions, how does it necessarily follow that h of x doesn't necessarily follow that h of x equals f of x, g of x is also convex. Give a proof or a counterexample. Okay, so yeah, this answer is no, not necessarily. Why is it the case? Because we never heard of it, right? It just doesn't hold. If it was a thing, we definitely would have heard about it in a theorem. So we're just going to think about what kind of counterexample we can use. So we're going to just make both f and g convex. Let's just say x squared and x squared minus 10. Why did we do minus 10? Because we kind of want to construct something where before we had something of the second derivative positive, and then somehow we have to make it negative, right, for the product of it. So this is how we're going to construct it. H of x is equal to this thing over here, right? Because we just did x squared times x squared and minus 10, and we have this over here. We just take the first derivative, then the second derivative, and we get to this. So let's just say x equal to 0. Our second derivative of h is negative, which means that it's concave. So that even though f and g are convex functions that we originally start off, we kind of designed it such a way and we picked it such a way that like basically we would have this minus 10, which we and then we times it with x squared. So we're going to definitely get a negative term. And then we make sure that this negative term is big enough so that it becomes negative. So yeah, so then we get concave near the origin over here. And it's a counterexample. And then in part C, we have determine whether each of the following functions is convex, concave, or neither. Explain your answers. You may use standard results about convexity. So we're going to tackle one part at a time. In part I, we're trying to show that j is from 1 to infinity. G of x is taking two long functions. So what we can do for this is we kind of just write it out first, right? And then make sure we have the domain. Then we just take the derivative because you're going to always want to get to the second derivative to know if it's concave or convex, right? So the second derivative, if you were to take, this is just chain rule, classic chain rule, and you would get this. And then you take, apply chain rule again for another time, and then you get this, which simplifies down to this, I guess, slightly more nicer form. So we can argue that over here, ln of x is like x is greater than 1, so ln of x is greater than 0. But then that would mean that the top part, 0 plus 1 is 1. And then the bottom part is something squared, which would also be positive. So if something positive to a negative sign over here means that this term is always negative. So we're going to have a concave function. So yeah, that's part C, I. And for the second part, we have k is from this, and then we have k of xy is equal to x plus y divided by 1 plus xy. I guess it's a similar idea for this. We're just going to kind of do what we can to show what we need. So over here, we're going to kind of simplify it slightly because it's kind of hard to deal with a function with two variables, x and y, right? So we're just going to assume that we're on the line y equals x, so then we can make our life very simple by just having one variable instead. And the function becomes 2x divided by 1 plus x squared. And we're just going to call this function gx. I'm going to take the derivative of gx and take the derivative of g prime of x. This is just algebra. There's not much to talk about this. But essentially, the second derivative evaluates to this. So then what we can do with this is that we know that this function does something over here because for x from 0 to square root 3, it's concave, but for x greater than square root 3, we have something convex. So then it's neither. Why is that the case? Because we can kind of see what we can reason about this, right? We can see the denominator is 1 plus x squared. X squared is always positive because it's a square, right? And then 1 plus that is positive. So anything to the third power will still be positive. So the sign is really up to the numerator to decide. X times x squared minus 3, right? So the roots are 0, negative square root 3, negative square root 3. So then we have a function that kind of looks like this because it's just is like that. And if we were to map it out, there's a section that's negative and there's sections that are positive. So the sign changes and we know, okay, this is not going to work. So it's neither. And the next what we have is the last case, where we have this expression over here. We have the L is a function that maps a d-dimensional vector to a scalar. And then we have the following ATX to the third power, where d is greater than 1 and a is a fixed non-zero vector in Rd. Okay, so for this, what you can do is sort of the following. We kind of write down what we have over here, and we're just going to treat it as if we first define a variable for ourselves, UATX, right? You can be any value because we know that A is not equal to 0 in the condition. Yeah, I'm going to first go over the condition D is greater than 1, A is not 0, and then the following things, right? And that X can be anything. So if you have something of A and something of X, that can be anything. The result of U could still be any value because it's not equal to 0, right? So then we can just think of it as L of U, and then this is to the third power, right? And then we can take the derivative of that, and then the second derivative of that. So it means that if we have a thing that's U is positive, then this thing would be basically greater than 0. And if this thing was negative, this thing would be negative. So it really depends on what ATX is. And ATX, as we argued earlier, could be any value. So hence, again, this is neither. So I think we're at the end of this question. The major takeaway is that this is just using Taylor's theorem for part A. Part B is just mainly finding this counterexample. And part C, it's just kind of showing, okay, you're just taking, anytime we're asked about concave, convex, concave, neither, it's just going to the second derivative and constructing that function and not arguing if it's greater than 0 all the time or not, or other cases.